In this video, we'll be looking at more examples of graphing polynomial functions. Let's start with example C. We want to sketch the graph of the polynomial function f defined by f of x equals -2 times x plus 3 squared times x minus 2 squared. From our previous video, we learned that if we want to draw the graph of polynomial functions, we should follow 3 steps. Our first step is to determine the end behavior for our function. To figure out the end behavior, we need to identify the leading term of this polynomial. We need to think, if we were to multiply all of these factors out, what would be the leading term? Well, first, let's write out the factors. We have f of x equals -2, and then we have 2 copies of x plus 3, 1 copy of x, and then 2 copies of x minus 2. To find the leading term, we want to multiply together the term with the highest power of x in each of our factors. So that's going to be the -2 times x times x times x times x times x. So altogether, that gives us -2 x to the 5th power. So what this means is that our polynomial function will behave more and more like -2 times x to the 5th power when we trace our graph to the right and when we trace our graph to the left. So let's get a sense of what -2 times x to the 5th power looks like. We've learned previously that when we have x to an odd power, it has this sort of shape. So this is x to the 5th power. -2 times x to the 5th power means we're applying a vertical scale by a factor of -2. The negative portion means we're doing a vertical reflection. The 2 means we're stretching our graph. So -2x to the 5th would look something like this. So if we want to know what happens when we trace f of x to the right and to the left, all we have to do is trace this blue graph to the right and to the left. So as x goes to infinity, meaning as we trace our graph to the right, our blue graph here goes down. So we would write that f of x will go to -infinity because our function will behave the same way. It'll go down. And as x goes to -infinity, meaning when we trace our graph to the left, well, for this blue graph, when we trace to the left, it goes up. So since our function behaves the same way, we'll write that f of x goes to +infinity. It'll go up. Now that we've determined the end behavior, we can move on to our next step, which is to find these x-intercepts, or the zeros of our function, and also their multiplicities. To determine the zeros, we can use the factor theorem, which tells us that if our polynomial has a factor of x minus some number, then that number is one of our zeros. So in our polynomial here, we have x plus 3, which can be thought of as x minus -3. So -3 is one of our zeros. And since we have x plus 3 squared, the multiplicity of this zero is 2. Our next factor is just x by itself, but x by itself can be thought of as x minus 0. So 0 is one of our x-intercepts. And since we have just x to the first power here, the multiplicity is 1. And lastly, we have a factor of x minus 2, which tells us that 2 is one of the zeros of our function. And since we have x minus 2 squared, we know that 2 is a zero of our function with multiplicity 2. Now that we've determined the zeros and their multiplicities, we're ready for our third step, which is to sketch the graph of our function. Let's start by drawing our axis, and we'll only mark down locations on the x-axis. Since this is just a sketch, we don't really need to be too precise with the y-axis. Now that we have our axis down, let's plot the x-intercepts. We have an x-intercept at -3, at 0, and at 2. Next, we want to go to our leftmost x-intercept and think about what happens if we continue to the left. Will the graph go up or will it go down? To decide which of these we'll draw, we want to look at the end behavior. The end behavior says that as x goes to -infinity, f of x goes to +infinity, meaning when we trace our graph to the left, the graph goes up. So we're going to draw something that goes up. Drawing this, we have something that looks like this. Next, we want to connect all of our x-intercepts together. But to go from one to the other, we need to pay attention to how our function behaves at the x-intercepts. At x equals -3, there are two options of what the graph will do. The graph can either cross the x-axis or it can touch the x-axis and bounce off. Its behavior will depend on the multiplicity of our zero. At x equals -3, the multiplicity is 2, which is even, which means that our graph will touch the x-axis and bounce off. So let's draw that on our graph. Next, we want to connect what we have to our next x-intercept. So bring the graph back down towards x equals 0. Now that we're at x equals 0, we want to think, will my graph cross the x-axis or will it touch the x-axis and bounce off? And again, to determine this, we'll look at the multiplicity. At x equals 0, the multiplicity is 1, which is odd. When the multiplicity is odd, the graph crosses the x-axis. So let's draw our graph crossing the x-axis. And next we'll connect it back up to the next x-intercept. And at this last x-intercept, the graph can either cross the x-axis or it can touch the x-axis and bounce off. At x equals 2, the multiplicity is 2, which is even, which means our graph is going to touch the x-axis and bounce off. So this will finish off our graph. Notice that this last segment that we drew is consistent with our end behavior, which says that as we trace to the right, the graph goes down. This is how we use the end behavior along with the zeros and multiplicities to help us draw the graph of polynomial functions. Let's look at one last example. We have the function g here defined by g of x equals x minus 1 squared times x squared minus 9 times x squared plus 4. So first, let's try to determine the end behavior for our function. To determine the leading term, let's write out our factors. We can think about g of x as x minus 1 times x minus 1 times x squared minus 9 times x squared plus 4. We can find the leading term by multiplying together the term with the highest power of x that's in each of the factors. So that's going to be x times x squared times another x squared. So altogether we have x to the 6th power. So that's our leading term. This tells us that when we trace our function to the right and to the left, our function will behave just like x to the 6th power. So let's get a sense of what x to the 6th power looks like. Since we have x to an even power, we know that its graph looks like a U shape. And so, as x goes to infinity, meaning as we trace our graph to the right, for x to the 6th, the graph goes up. So our function g of x will behave the same way, which means that g of x will go to positive infinity. And as x goes to negative infinity, meaning as we trace our graph to the left, well, if we trace this x to the 6th graph, we see that it goes up. And so our function g of x will behave the same way, which means g of x will go to positive infinity as well. Now that we have the end behavior for our function, let's move on to our second step. We want to find the x-intercepts or zeros of our function and their multiplicities. This time, however, we can't immediately use the factor theorem because looking at the factors of our polynomial, it's not all written in terms of x minus some number. We can rewrite our polynomial, though, by factoring it a little further. So factoring this some more, we see that g of x is x minus 1 squared. The x squared minus 9 is a difference of squares, so that can be written as x plus 3 times x minus 3. And then lastly, we have x squared plus 4. But I can't really factor that any further, so we'll just leave it as x squared plus 4. Because we have this x squared plus 4 factor, this doesn't quite look like x minus some number. So instead of using the factor theorem, we can always find x-intercepts by setting our function equal to 0 and solving for x. So setting our function equal to 0, we have x minus 1 squared times x plus 3 times x minus 3 times x squared plus 4 equals 0. And when we have a product of things and it equals 0, what we can do is we can split up each factor and set them each individually equal to 0. So we have x minus 1 squared equals 0. We have x plus 3 equals 0. We have x minus 3 equals 0. And lastly, we have x squared plus 4 equals 0. If I wanted to solve the equation x minus 1 squared equals 0, we can first take a square root of both sides to get rid of the square, and then add 1 to both sides. This gives me x equals 1. In the equation x plus 3 equals 0, all we have to do is subtract 3 from both sides to get x equals negative 3. In the equation x minus 3 equals 0, all we have to do is add 3 to both sides, which gives us x equals positive 3. And then lastly, if I want to solve for x in this last equation, we might start by subtracting 4 from both sides. So this gives us x squared equals negative 4. And then to isolate the x, we would take the square root of both sides. But this is where we run into some problems. We can't take the square root of a negative number, so from this equation, there are no solutions. So in the end, the zeros or the x-intercepts for our function are 1, negative 3, and positive 3. The factor x squared plus 4 does not give me any x-intercepts. Now let's go back to the factored version for our polynomial to determine the multiplicities. Since we have x minus 1 squared, we know that 1 is a 0 of g with multiplicity 2. Next we have x plus 3, and it's just to the first power, so negative 3 is a 0 of g with multiplicity 1. And then lastly, again, we have x minus 3, and it's just to the first power, so 3 is a 0 of g with multiplicity 1. Now that we've determined the zeros and the multiplicities, we're ready to draw our graph. Let's start by putting down our axis, and then we'll plot our x-intercepts. Our x-intercepts are at x equals 1, x equals negative 3, and x equals positive 3. Let's now go to the leftmost x-intercept and decide, will the graph go up or down as we continue to the left? The end behavior tells us that as x goes to negative infinity, g of x goes to positive infinity, meaning when we trace our graph to the left, the graph goes up. So let's draw a segment of our graph going up and to the left. Next, we want to decide what the behavior of our function is at the x-intercept negative 3. Will the graph cross the x-axis, or will it touch the x-axis and bounce off? At x equals negative 3, the multiplicity is 1, which is an odd number. So when the multiplicity is odd, we know that the graph crosses the x-axis. So let's draw our graph crossing the x-axis and then connect it with the next x-intercept. So now that we're at x equals 1, we have to decide, will the graph cross the x-axis or will it touch the x-axis and bounce off? At x equals 1, the multiplicity there is 2, which means that it's an even multiplicity, so the graph will touch the x-axis and then bounce off. So let's draw our graph touching the x-axis and then bouncing off, and then connect it with the next x-intercept. Now, at x equals 3, we have to decide once again, will the graph cross the x-axis or will it touch the x-axis and bounce off? At x equals 3, the multiplicity is 1, which means that our graph will cross the x-axis since it's an odd multiplicity. So the last segment of our graph looks like this. And once again, this last segment that we drew here is consistent with our end behavior, which says that as we trace to the right, the graph goes up. So we're now done sketching the graph of our function. In this video, we got some more practice with drawing the graphs of polynomial functions using the end behavior along with the zeros and multiplicities.